having me come speak. This talk is a conglomeration of several talks I've given previously that are all in this folder. So we'll see how the ordering goes. But I am talking about orbifold, so I should first of all tell you what is an orbifold. Okay, so what is an orbifold? It's a space. It's locally modeled on balls in Rn modulo isometries of Rn. So let's think what the local space looks like. So it might have, so a manifold, remember what's a manifold?
It's locally modeled on Rn.
It's locally modeled on Rn, good. So an orbifold is a generalization of a manifold. So all the manifolds, they're examples of orbifolds. So here's examples. Every manifold. Okay, here's another example. The barber shop. Orbifolds all have cool names because they're cool. So you've been in a barber shop where they have a lot of mirrors, and they got a mirror here and they have a mirror here. So you're actually in an orbifold, and you're looking at it and you're like, whoa, come, right? That's the barber shop. So it's like a hall, and then this one's mirrored, and that one's mirrored. Okay, so what do I mean by mirrored? So what are some of the ways? So this is a three-dimensional orbifold. Here you are in your barber shop looking at the two mirrors. So so it's modeled on a little ball like this. So these points in the middle here are modeled on just a regular ball, where the group of isometries of Rn is just trivial in the middle there. And then when I'm at one of the mirrored, part of the mirrored locus, looks like a ball, modulo just a reflection in Rn. Okay, so that's why it's called the reflection locus, because the isometry group actually acts by a reflection. So modulos, there's different actions of Z2 on this ball, but there's one that's reflection. So that's going to look sort of like this, where this side is mirrored. Okay, sort of mirror it to indicate what the action is there. So every point in this barber shop, which is just two mirrors and a slab with mirrored walls, is either modeled on a regular little ball where the isometry group is trivial, or where the isometry group is Z2. Here. Okay, what's another three-dimensional orbifold? So one thing I could do is I could take some knot. Take a knot. Try to take a non-trivial knot. Let's see if I make one. There's a knot. It might be non-trivial. So now I'm going to take the knot and I'm going to label it too. So what do I mean by that? So what I mean is I take S3, I take this knot in S3, okay, and around the knot I'm going to make that a non-trivial orbifold locus. So everywhere around here it looks like the neighborhood locally looks like Rn, like a little ball, it's a manifold. And right here, what does it look like? Right around some point on this knot, the neighborhoods look like a little ball, modulo Z mod 2Z, but this time the group's acting differently, right? It's acting by rotation by 180 degrees, right? So it sort of looks like the quotient now has the same underlying space, but it has this little line here where the action is non-free.
Are these solid balls or the surfaces of the sphere?
They're solid balls. Okay, so it's like a little ball. So this is a solid open ball, so it's actually, open ball is the same as Rn, homeomorphically.
What do you mean by non-free?
So action is free if it doesn't fix any point. And there's some points in this ball that are fixed by this action. That little core right there, so it's not free. Okay, so that's locally what this is modeled on. That's what the space looks like. Okay, so the set of points that are locally modeled on BN, locally modeled means they have little neighborhoods that are locally modeled on. BN mod gamma, where gamma is non-trivial, that's called the ramification locus.
Okay, does that mean that it's the set of points that don't have a neighborhood that are just modeled on BN?
That's exactly right.
Okay.
So if this group is trivial, then this is just modeled on BN, so it's like a manifold. So, or a manifold has an empty ramification locus. So that's another definition of a manifold, is an orbifold where the ramification locus is empty.
You know, can it be different gammas for different balls that we're
Good point that I'm trying to avoid. So no, manifold, you told me the definition of a manifold was that it's locally modeled on Rn. But you totally ignored all that heebie-jeebie about the overlapping maps, blah, 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 right? So we have the same thing going on with orbifolds, okay, except it's more complicated. Okay, so I have overlapping maps, so there could be, yes, it's true, there could be different ramification locuses, different points. So the answer to your question is yes. And I need to make sure that the ramification locus behaves nicely with how these, so I could have like a 3 here, for example.
So we want, like, what?
So you
Isomorphic
want,
subgroups or
so
something?
that's right, so you want when they overlap, for there to be a little neighborhood of points in the intersection where it's so where you have like injections of that group into both of the 2 groups of the bigger one. Okay, so I'm ignoring those details, but you do have to worry about those. Okay, so just like for manifolds, when you have overlapping maps, you have to worry about it. For orbifolds, you have overlapping maps, you have to worry about it being homeomorphic, and also that the groups behave nicely with respect to those overlapping maps. Yes, question?
Do you have to be discrete?
Yes, so it's a discrete group of, so not the whole isometry group, but a discrete group of. So actually, you want it to be a finite group of. Okay, because you're fixing some point. Okay, good. So now what am I doing? Okay, the underlying, so here's some definitions, the ramification locus, the underlying space. You just forget the groups. Okay, so you forget the ramification locus. You don't erase those points, but you erase the fact that so the orbifold has this extra structure telling you what the group is here, and you just forget that, and that's called the underlying space. So let me do some more examples.
And it's a topological space.
Yes, it's a topological space. Okay, so let me do some more examples because you're going to be happy. Let's go down to 2 dimensions for a minute. But there's some really interesting things going on in 3 dimensions. So for 2 dimensions, what are some things that I can have? So I want to take a little disk, and I say, what kind of finite isometry groups of R2 can take this disk to itself, fixing that point? So one thing I could do is I could rotate by, say, 2 pi over n. Okay, so what's the quotient going to look like in this case? So suppose I rotate by 2 pi over 3, so like a little fundamental domain for this action is one of these things. Okay, so the quotient space is going to look like this disk, and then I'm going to glue together this side and this side because the rotation by 2 pi over 3 is going to glue this edge to that edge. Okay, so it looks like a little cone. You can actually cut it out. I should have cut one of these out. You can cut out an angle of 2 pi over 3 and then glue them together and you'll get a little cone. So I can actually do that with my piece of paper. I'll do it with my notes because they're not very useful. Here, I'll do it with 2 pi over. So what angle is this? Well, it's supposed to be, I just folded the paper in 4, so it should be about pi over 2. It should be about right.
Oh, I see. Yep.
So now what I'm going to do is I'm going to glue these edges together and see I get a little cone point there. Okay, so there's a ramification locus right there. Okay, so this is called a cone point. So points that are locally modeled on a little disk modulo a cyclic group of rotations are called cone points. Okay, and if I want to restrict myself to orientation preserving isometries, this is all I'm going to be able to do. So here's some examples of orbicals that I can get. So one thing I could do is I could take a little cone and I could glue a disc onto the other side, like this. So I can take one of these cone points. So notice when I glued these two edges together, this boundary is going to be a circle here. Okay, so if I could just glue a disc onto it. Okay, this is called a teardrop. And it's bad.
Too sad.
Bad. Bad means it doesn't have a cover that's a manifold. Okay, so I'll talk about what's a cover in a minute. It's sort of what you think it should be. Okay, so let's do a football. We all know football is good. So here I have here's 3, say. Okay, so this is a football.
So when you're labeling with integers, that means that those are cone points of 2 pi over.
Exactly. So this is my shorthand for cone points. Okay, so this means that this point is locally modeled on a disk onto a cyclic group of rotations of order 3. Okay, so this is covered, this is good. So this is covered by a manifold. So I can take a sphere and then rotate by 2 pi over 3 to the sphere, right? It's good. That's going to have some fixed point. That's not a manifold covering, but it's an orbifold covering. So to give the definition a little bit. And so this is covered, and this is a quotient of a manifold by some group, and in fact, it's a little bit stronger than being covered. Okay, so this is a good orbifold. So now we can get lots of orbifolds just by looking at surfaces and then taking some group action on the surface, and we'll get some orbifold. Like for example, I can take the torus. This is one of my favorite orbifolds. I can skewer it. Okay, so if you took a donut and a kebab stick and you stuck it right through the donut, right? But you don't, the interior of the donut's not there, you should ignore that part. Okay, so this is the surface. Okay, now I'm going to rotate by 180 degrees around that skewer. Okay, then I'm going to take the quotient. Okay, so what am I going to get? So it's just going to be the bottom part of this. It's going to be a fundamental domain, like this. Okay, and that rotation is going to identify this edge with that edge, and this edge with this edge, like this.
Does the line that you're cutting the torus with, does it have to go through the center?
Well, the way that I drew my torus, yes. Okay, so I wanted to take, I'm just making this be an isometry. Like in general, you don't have to be this geometrically explicit, but for the way that I did this, yes. Okay, so now what happens, I glue these up. So now I've lost the geometry, right? But topologically, okay, this thing, right, so its underlying space is a sphere, so topologically, it's just a sphere. If I forget the fact that these were fixed points, it's topologically a sphere, right? Because I started with this little open tube and I glued the two tops together. Okay? So it's topologically a sphere and it's got 4 cone points of order 2 on it. Okay, so this is a quotient of the torus by order 2 action. This is called S2, so underlying space S2, with 4 cone points of order 2. 2, 2, 2, 2. Okay. So let's do some real serious improv here. So remember the torus, its universal cover was R2. Okay, so this S222 is generated to the group, so you could think of this as a group acting by rotations of order 180, right? So I want in the midpoints of these lattices, this unit, like lattice here. Okay, so this is the group. Let's see if I can do this here. So what's a fundamental domain for this? Action. So I think it's one of these things. So let's try this and see what happens. I think that's a fundamental domain. So this gets rotated around. What happens to this under this action? So did everybody see what action I'm describing? Okay, so this gets rotated around 180 degrees here, so that's going to bring it to this one. Right, and this gets rotated 180 degrees, which is going to bring it to this one. And this gets rotated 180 degrees, which is going to bring it to that one, so I'm covering up everything. That's right. Okay, so I think that's right. I haven't done this in a while.
When you say the half integer lattice, is that only?
So just these points.
Okay, not the proper integer one?
No.
Okay.
And when you say a fundamental domain, that means an area that you can cover the entire space by choosing the group action?
Exactly. And it just overlaps on its boundary.
Okay.
To make sure that that's the right one. Okay, you should check to make sure that's the right one. Okay, but this realizes the orbifold, so this orbifold, note S2, 2, 2, 2, 2, okay, is a quotient of Euclidean space, meaning I care about the metric, by isometries. Okay, so this puts a geometric structure on this orbifold. Okay, note that geometric structure is really different from the geometric structure for S2. Okay, I cannot get S2 as a quotient of R2 by isometries. Okay, so they have different geometries. So when I add the ramification locus, it completely changes the geometry of the orbifold. Yes?
I'm just curious, you saying to check that it's the right fundamental domain? Does it?
Oh, I need to make sure that it doesn't come back on itself.
Oh, okay. So it doesn't matter, like, if you had two different fundamental domains?
Oh yeah, no, that would be okay. Check that it is a right fundamental domain, a correct fundamental domain. I think it is. Okay, so to do that, I need to check to make sure that it doesn't come back and hit itself like this. Okay, and then you need to think how this folds up too. Okay, so also, while I'm giving homework problems, see how this folds up.
Was every orbifold guaranteed to have at least one correct fundamental domain?
Well, it's not geometric. Okay, so it might not have any manifold cover like this one, this bad orbifold. No, it does not. Okay, so it does not have a manifold cover, so I can't model it on some nice geometric space. And by nice geometric space, in 2 dimensions, I mean E2, S2, or H2. I can't model it on that space, quotiented out by some group of isometries. Okay, for that one, because there's no manifold cover. Okay.
So, since we're now getting the S2, 2, 2, 2, 2, by modding out by this group isometries, then that orbifold has a Euclidean metric on it.
That's correct.
Okay.
Okay, that's a good point, so that I didn't mention. So that orbifold has a Euclidean metric on it, right? And what's that Euclidean metric? I just take 2 points above it in the fundamental domain, and I take the distance in Euclidean space. Okay, so that says this is a geometric orbifold.
I mean, in the fundamental domain, or just the shortest distance between the two pre-image points?
That is the same thing. So I can take a
you can
fundamental
have-
domain that contains it. Okay. So now let's talk about, okay, so we did S2, right? So this one, its universal cover is S2. Okay, so it's a cover. I haven't told you what a cover is, just ignore that. Okay, this is an orbifold cover, right? So I took some orbifold, I did some isometries to it, and its quotient was this thing. Okay, and this is simply connected, so this is modeled on S2, so this is a spherical orbifold. Here's a Euclidean orbifold. Where's a hyperbolic orbifold? That's what you all want to know. Okay, so this one I think I can do a little bit better, so let's think. So what's a hyperbolic manifold? Okay, what's hyperbolic space? Hyperbolic space is a disk. The geodesics in the disk are circles, pieces of circles that meet the boundary of the disk perpendicularly. Okay, there's some metric you can put out, just ignore that. Okay, and then the isometries are Mobius transformations. Okay, so they're going to take circles that are perpendicular to this to circles that are perpendicular to this. Okay, so they take geodesics to geodesics. All right, so I can take a fundamental domain for a puncture torus right here. So these points at infinity, they're not here. And it's going to take this geodesic to this geodesic, so it's going to glue this up like this, and it's going to glue that up like that. Okay, the quotient manifold is a puncture torus. I'm going to have to do the Euclidean torus again in a minute. I'm not happy with it. All right, so now.
So, I mean, you call it the puncture, everyone calls it the puncture torus, but is that the same as actually taking a closed torus and puncturing it? Is that homeomorphic?
What do you mean the same?
Is it homeomorphic? Is it
Yeah, it's
topological space?
homeomorphic, right. So you just remove, the thing is you just remove one point, you don't remove a disk.
Right, but I mean, the way you draw that always like implies a
Yeah, it
a
implies
boundary
a
thing.
geometry, right, that comes
Yeah.
from this geometry, but it's just hard to draw one point removed.
Right.
So that's why you do that, but topologically, it's just a torus. I mean, but why do I draw a torus like this? Like, that implies some kind of geometry too. Like, why don't I just do a crazy torus, you know? I don't know how my torus go like this. And then I take away one point.
It's a pi torus.
Okay, that's the puncture torus. Okay, so I drew it with some kind of geometry, right? But it's the same thing, okay? But topologically, so here, right?
Or it's a dinosaur torus.
Okay, so let's just ignore that. Get back to our old, happy, friendly world. Okay, so I can take this torus, and I'm also going to skewer it if I happen to have a hyperbolic torus lying around. To think where I can get a hyperbolic torus. So I'm going to skewer it, and where one of the points is infinity. Okay, and then again I'm going to do a 180-degree flip. Okay, and what's going to happen? What's my quotient going to be?
Would it be that with one fewer cone point?
That's correct. It'll have one fewer cone point. What about the underlying topological space?
It should be H2, or, well, it should be something hyperbolic.
Yeah.
Now, the underlying topological space might not be hyperbolic, right? Because here, the underlying topological space is S2. That's not Euclidean. Okay, so the ramification locus really changes the geometry. So what's the underlying topological space? Let's think. So we've got this.
Punctured sphere.
Yeah, it would be.
A
just
punctured
R2.
sphere, good. What's a punctured sphere?
R2.
It is a disk, right? So I have the quotient of this thing, where I glue these together. So I kind of like just glue this together and off into infinity. Okay, and then I glue these two together here. Okay, so I get, it's hard to draw, I'll just draw it like this. to talk about. Okay, but it's a sphere minus a point. Okay, so the point I removed, so one of the points that I fixed was one of these. So you can think of going from there, from S2, 2, 2, 2, 2 to, that's going to be called S2, 2, 2, 2, to infinity, just by removing this point. Okay, so this is called S2, 2, 2, 2, to infinity. So infinity refers to the fact that this is a cusp in the hyperbolic structure. Okay, so how am I going to get this?
Sorry, I'm still a little confused on that.
Uh-huh.
Where's the infinity point in the picture you've drawn?
It's out here. So I drew it as a, so here's how I cheated. Instead of drawing this as a cusp, I drew it, I removed a little neighborhood of it and drew it like this. Okay, so that is actually topologically different. So really, if I wanted to draw it in its cusp glory, I should draw it like this. So the boundary of that disk, I just took the boundary of that disk, I erased, sent it up to infinity, and then there's 3 points here.
Okay.
It's a little bit better picture. Okay. So now I can talk about, and I just completely deviated from my notes.
And that's the underlying topological space of that is S2?
No,
No.
no, well, it's S2 with a point removed. Okay, so that's what that cusp is. So, or if you want to remove a little neighborhood of this, you can think about it D2, 2, 2, 2. That's what I would get if instead of taking the quotient of this cusp torus, I took the quotient of this torus where I removed this thing. So that's a subtle difference. Okay, but it is a difference.
So topologically, the puncture and the cusp torus are exactly the same.
Well, it depends on, one is a manifold with boundary, and one is a manifold without boundary.
Okay.
Okay? So I can think of my, so my disk is really a sphere where I removed a little open disk. Okay? And then this cusp thing is a sphere where I removed 1 point. Okay, so one has boundary and one doesn't. Okay, so just think of it like S2, 2, 2. Just think of that. Sort of the right way to think about it. Okay. So now I'm going to try to give this to you as a it's very similar to this picture right here. Okay, so here, I'll pass this around. Here's a little fundamental domain for punctured torus. Right here. So what you want to do to this, I'll show you what to do to it so you can look at that. Anybody can draw this that wants to. So I'm going to take this, let me give a concrete example. Okay, so here's a fundamental domain. Okay, so I'm going to add the flip z goes to -1 over z. So no, this is, actually, I'm going to remember that. So here's what I'm going to do. I'm going to take 180-degree turns in these 3 geodesics. Okay, so this picture, what this is going to be really similar to what was going on over there. What I'm going to do is I'm going to take the isometry of hyperbolic spaces that takes this geodesic to itself, it takes this side to this side, so it's going to go like that, and it's going to flip everything, it's going to rotate by 180 degrees around this point.
Okay, so we're going to...
So that's going to move this fundamental domain down to here. Okay. All right, and then I'm also going to take the one that's 180-degree flip around this point and 180-degree flip around that point. Okay, so what's that going to do? So how is that going to close up this? So let me just think about this fundamental domain and how the action is on that. Okay, so this is going off to infinity. So when I glue these things together, I'm going to get a cone point of order 2 right there. Okay, this is locally modeled on R2. Okay, this is homomorphic to R2. Rotated by a group of order 2 that's just rotations. Okay, so these two things are going to glue together. So this one's going to glue to that one. This one's going to glue to this one. This one's going to glue to that one. Okay, that's how this group's going to act. So then I can keep tiling hyperbolic space by these. Okay, so what is this gonna do? It's gonna take this is actually an isometry of hyperbolic space, okay? It's gonna take this fundamental domain and it's gonna flip it around to this fundamental domain right here. And this rotation in this point is gonna take this fundamental domain, it's gonna flip it around to this one. Okay, so it's gonna keep flipping around like that. So here I have the tiling by the fundamental domain. Isn't that beautiful? All right, so now, okay, so I said this was covered by a punctured torus, right? Okay, so where is, okay, so what is this group, by the way? So this is some group.
So are you claiming that this is a cover of S2, 222 infinity?
Okay, so in particular, I'm claiming that this is S2, 2 to infinity is a hyperbolic orbital. Okay, about the question of this. Now, what is this group? So this is some group acting on hyperbolic space. What is it?
D2? No.
Okay, what are some things in the group?
3 reflections.
Three
Three
rotations, right? So this is like a Z2. This is a what?
Z2.
And this is Z2. So this, and how do these Z2s interact? So what happens? If I do this Z2 and this Z2 and then one the other and one the other, one the other, am I ever going to get to the identity? No. And what about the other ones? Okay, so this group, this is something to prove, this group, the group acting on H2 is actually acting by isometries is Z2 star Z2 star Z2. Okay, and Z2 star Z2 star Z2. Okay, and this, oh, by the way, this is the orbifold fundamental group. Okay, so if you're in my algebraic topology class, we spend a lot of time, yada yada, defining fundamental group. Okay, but the orbifold fundamental group, one way to define it is to just say, take the universal cover, okay, for a good orbifold, I'm going to do a good orbifold. Take the universal cover, and that group acting on the universal cover to give you the space is the fundamental group. So phi 1 orb equals the group which acts on the universal cover and with quotient the orbifold. Okay, so that says this is an orbifold with fundamental group Z2 star Z2 star Z2. Okay, so we want this notion of fundamental group to go well with coverings. So I claim that this was a quotient, this S22222. This was a twofold quotient of the punctured torus. Right? Okay, so how do I get the punctured torus lying in this picture? So where's the fundamental domain for a punctured torus here?
It's 2 of the triangles.
Take 2 of the triangles, right, and I'm going to get a punctured torus. What's the fundamental group of the punctured torus?
The orbifold fundamental.
Just the fundamental group or the orbifold fundamental group, they're the same in this case because it's a manifold.
Z star Z.
It's Z star Z, good. So there is an index 2 subgroup of Z2 star Z2 star Z2 consisting of words of even length That's how you know it's index 2. Okay, and what is it? Which is free on 2 generators. Okay, so this should be making you happy because you've got a free group on 2 generators sitting as a subgroup of this orbifold group. Oh, and that corresponds to this cover of the orbifold. Okay, so this is a sort of kind of hand waving over what an orbifold cover is here. Okay. That was the hardest thing I'm going to talk about. I also want to talk about some other things that can happen, some other hyperbolic orbifolds that are cool. And I like that one because I like the group Z2 star Z2 star Z2. The same thing if I think about for the Euclidean case, if I think about there's an index 2 subgroup of this that is Z plus Z. Okay, so now some other hyperbolic orbifolds. Okay, so for, oh wait, first let me do some other spherical orbifolds first. So here's some triangle groups I can get. So I can take spherical orbifold. So now I'm going to take this, I'm going to rotate out by, say, what do you want me to rotate out by?
2 pi over
2 pi over 3. Okay, so this is going to give me the football with 3. Okay, now I'm going to take this, and I'm going to quotient out by another rotation that just takes this 3 to that 3. Okay, so now I'm going to quotient out, and what's that going to give me?
teardrop.
Gotta think what's gonna happen. So how many order 3 cone points am I gonna have if I identify that one with that one?
You're gonna have an order 3 and an order 2.
2 order 2s.
I've got the skewer going through, bing, bing, right there.
Yeah.
Okay, so I'm gonna have 2 order 2. Okay, so this is gonna be underlying space. What's the underlying space gonna be? That's 2, and there's gonna be an order 3. And then there's gonna be a 2 and a 2.
Where's the second one?
What'd you say?
Where's the other order 2 come from?
So it hits it twice. It hits it here and here.
Oh, okay.
And I'm going to identify this. So a fundamental domain is like this, with the 3 right here. Because I made this side go to that side. Right, and then I have to glue this to that. And that's going to give me order 2 components there.
If you would reflect it through a plane instead
Okay,
of
great. Okay, so let's do that. So I could do that, and then what am I going to get? Suppose I reflect through a plane, right? This is going to be all mirrored. But I could actually reflect through this plane, so I could take so let's think about what this fundamental domain, what's going on over here. Okay, so I've got, keep in mind, totally improv. So I've got these 3 things going here, where those are all at angles of 2 pi over 3. Okay, does that make sense what I'm doing here? That cuts it up like that. Okay? And then I'm going to cut it up with the order 2 through here. So I wanted to talk about reflection. Right? Right, so I could take an orbifold that was just this space right here, this triangle, this spherical triangle, and it was just mirrored all along here. Okay, so we have an orbifold. Okay, so now let's think about the ramification locus here. Okay, so it's going to be 2. These are going to be mirrors all along here, so these are all 2. Okay, what's going on here? So these are like corner reflectors. So these are called corner reflectors. So this is what I can do if I start thinking about reflection. So this is typically called like triangle groups. This group's called a triangle group, or like a reflection group sometimes, triangle reflection group. So it's really a triangle. And what group is going on here? I've got like reflection to this angle, reflection to that angle.
Z2 cross Z2.
Yeah, but what's the, so if I have reflection, we should have done the Euclideans first. So I have reflection through two lines.
You get a dihedral.
You get a dihedral group. Okay, so this gives you a dihedral group. Right? So it's like A, B, such that A squared equals 1, B squared equals 1, A, B to the n equals 1. That's what I think of as a dihedral group. Ding, 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 ding. What happens if there's no relation like this? What group do I get?
Z2, 3, Z2.
Z2, 3, Z2, often called the infinite dihedral group. Okay, this. Okay, so these, the group is a dihedral group. Okay, so that's something really interesting that can happen with even two-dimensional orbifolds. Okay, I get dihedral groups as a group that fixes a point. Okay, so now.
Okay, sorry, I guess my question was more, you've got an entire edge that's kind of.
That's right. So this whole thing is a ramification locus.
Right.
So this sort of goes back to John's question about how do these groups fit together. Okay, so here I've got a dihedral group, here I've got a reflection group, and here I've got a dihedral group. Okay, this reflection group embeds in both of those groups. I am being sloppy about this, but you don't want to see the whole little diagram. Okay, but this is just to say what kind of interesting things can happen in the ramification locus. So I can do this, this is modeled on spherical geometry. It's a fundamental domain. This group can act on the sphere. Okay, or I can have this act on an Euclidean space. Let's see Euclidean space next.
Sorry, before we move on away from the football, can you have a football with different numbers on each point?
You can have a thing with different numbers on both points. Okay.
Would it still be good?
It's not good.
You just build it locally.
Yeah, you just build it locally, that's right. But it's not good, so it's not spherical. Okay, so let's see. So now I'm going to take, what do I want to do? Okay, so I'm going to take reflection and, oh, I might as well take all these lines. I'm going to take reflection and all these lines that all meet up perfectly. Okay, so what's a fundamental domain for this action? Here. Okay, so it's like a shining triangle. It's got mirrors on both sides. Right.
All three of those sides are identified, right?
No, not if I take the reflection. Okay, so there's an index 2 cover of this. That's the well, it used to be called a turnover. I'm talking about three things at once. It used to be called a turnover, but now it's called a 3D Dorito. Just serious, 3D Doritos are orbifolds. Have y'all seen 3D Doritos? They're orbifolds. I'm pretty sure they're 3 orbifolds.
I remember the Doritos.
So
Yeah, from like the late 90s something.
oh, I thought they were current. That shows how far behind I am.
Aren't they people?
No, they were like Doritos, but they were kind of like puffed.
They're orbifolds.
Only in Mexico.
No, you can get them here.
Okay.
Okay, so this reflection orbifold, instead of doing the quotient, so where this is 2, 2, 2, okay, has a cover, has a twofold cover, orbifold cover. I still haven't told you what it is, and too bad I'm running out of time. I won't be able to give you the full gory definition of orbifold cover. Okay, but here's how I'm going to do it. I'm going to take 2 of these, I'm going to glue them together right along here. So I take 2 of these. I take 2 of those little things, how can I glue them together? So this was 244, right? So I should- There's the two of these. Right? So I'm gonna puff it up. I'm just gonna glue it together on its side. Okay, and this is 2, 4, 4 triangle. So this is called a turnover. So this is S2, 2, 4, 4. Okay. So if I take two of these, you see the angle here, right? It's locally modeled on pi/2 mod 4. This one's locally modeled on pi/2 mod 4. This one will be locally modeled on pi/2 mod 2. I took two of them right there. Okay, so this cover, which I'm not drawing very well, but really I should just draw it as 2, 4, 4. Okay, is again a Euclidean orbifold with underlying space S2. Okay, and it twofold covers this reflection orbifold, which is the triangle orbifold, which is generated by what's commonly called a triangle group, which is reflections in the sides of this triangle. Okay, I can also do this in hyperbolic space. So I've told you like about 500 orbifolds, so I'm really going over a lot of the details really quickly. Okay, so in hyperbolic space, you can tile with lots of crazy things. Okay, for example, you can tile with a triangle, a 2, 3, 7 triangle. Okay, where the angles are pi/2, pi/3, pi/7. Okay, so I found this. Okay, I've got so many pictures up here, and I should stop now. Is that right?
Sure. Next slide.
So this is from a program called Kaleidotile, which you can get on the internet. Very easy. I did it before my 9:30 class this morning. I was like, I have that program somewhere. I just re-downloaded it again. It takes like a second. So, and you can change the geometry from like spherical to hyperbolic to Euclidean, and it'll give you different tilings. So here's one of hyperbolic space. So these are all equal length segments in hyperbolic space. Because then I'm going out to infinity, it looks like more. And so there's this tiling by these things. So I could take like rotation of order, like I think this is 7 here, take rotation of order 2 here, rotation of order 3 there, and I'll get a 2, 3, 7 3D Dorito, or a 2, 3, 7 turnover. They used to be called turnovers. The Germans did it. It was like a puffy turnover. So turnovers. And then you can take the reflection group in this to get the 2, 3, 7 triangle orbifold. You can look at that. This one of my favorite ones. Here's a right-angled hexagon in hyperbolic space. Okay, so now I can take, these are right angles in hyperbolic space. So I can take the reflection orbifold generated by reflections in the geodesics that are the sides of this. And what's going to happen to these two reflections? So what's going to happen with this reflection and this reflection if I have a right angle? They're going to commute. Okay, so the group that I get is actually a right angle Coxer group, okay, on 6 generators. And all those generators are connected by an edge in the graph of the right angle Coxer group. Okay, so this is a particularly nice one. And I can have different geometric structures on this, so there's a whole Teichmuller space. This is just like name dropping. So there's a whole Teichmuller space for this right angle Coxer group here.
But are they all hyperbolic?
Yes, they're all hyperbolic.
So those are just different.
These are 2 different ones, 2 different realizations. And notice I have different isometries. People might want to actually see it. No one's going to watch the video.
What, 20 years from now?
That's right. Finally, we can give something to all the Cornell kids.
Oh, if she becomes famous, they'll probably make a viral video.
Okay, that's it. Bye. Bye.